Hi everyone, welcome to today's video brought to you by DJI Enterprise. My name is Michael Lee and I'm on the Solutions Engineering team. In today's video, we'll be covering map processing in FlightHub 2. For this workflow, we'll start inside an existing FlightHub 2 project and use mapping data that was already captured from a drone flight. Before we begin, it's helpful to understand where FlightHub 2 processing fits compared to DJI Terra. DJI Terra is still the better choice when you need more advanced processing options, local control, or additional output formats. FlightHub 2, on the other hand, is cloud-based, so you do not need a high-performance local computer to process the map. As long as you have access to FlightHub 2, you can upload the dataset, start the processing, and review the results from almost any computer. FlightHub 2 also makes it easier to turn the processed result into something your team can use right away. Once the map is processed, we can bring it into an analyzer, add simple measurements and annotations, and share it with someone else for review. This makes FlightHub 2 a strong option for workflows like construction progress tracking, site documentation, planning, and team coordination, where the priority is quick cloud processing and easy sharing, rather than advanced photogrammetry outputs. As we move through the process, we'll import the dataset, process a 2D map, bring that result into Analyzer, add a few simple measurements and annotations, and then share the Analyzer with someone else for review. The goal here is to share how a completed mapping mission can become something useful for project review, planning, documentation, and team coordination directly inside FlightHub 2. We'll start inside the correct FlightHub 2 organization and project. This is important because the dataset, process map, and analyzer will all be tied to this project workspace. Keeping everything inside the right project makes it easier for the team to find the data later and keeps the mapping results organized with the rest of the project resources. Next, I'll go to the project's resource library and select Import. For this example, the data was collected in the field and pulled from the aircraft's SD card because connectivity was not reliable on site. Since we're working from the SD card, I'll manually import the dataset into FlightHub 2. If this was a dock-based workflow with reliable connectivity, the data could be uploaded to FlightHub 2 automatically, reducing the need to manually transfer files from the aircraft. Here, I can choose whether to upload a file or a folder. For a mapping workflow, I'm going to upload the full dataset folder from the flight. This should be the original image data collected from the aircraft. Before starting the upload, it's a good idea to make sure the full dataset is included and that we're not missing any images. For the target path, I'll use all files. When uploading photos, only media files collected by DJI devices are supported. Once the dataset is selected, I'll start the upload. Depending on the dataset size and network connection, this may take some time. For this video, we'll move ahead once the upload is complete. Now that the data has been uploaded, we can create a mapping task. In the media files, we can see the uploaded folder here. I'll choose Start Mapping. For this example, I'm going to choose 3D mapping under Model Outputs. Once 3D mapping is selected, FlightHub 2 gives us a few additional settings that are specific to the 3D model processing. First, I'll confirm the mapping scene. For this walkthrough, I'll leave it set to normal, which is a good general starting point for a standard 3D construction workflow. Next, I'll review the region of interest option. If I only wanted FlightHub 2 to process a specific part of the captured area, I could enable region of interest and define the area to focus on. For this first map processing demo, I'll leave it off so the full selected dataset is processed. Next, I'll review the mesh model output. In this example, I'll leave mesh model enabled because we want FlightHub 2 to generate a textured 3D model that can be reviewed and measured later in the project or in the analyzer. For the mesh format, I'll keep B3DM selected. B3DM is a good default option for viewing and working with 3D model inside FlightHub 2. Other formats such as OSGB, PLY, and OBJ are also available depending on how the model needs to be used or exported. I'll also review the point cloud model option. For this walkthrough, I'm leaving point cloud model turned off since the primary goal is to create and review a 3D mesh model. If the workflow required a point cloud output for additional analysis, export, or use in another platform, this option can be enabled before processing. I'll keep the coordinate system set to known coordinate system and confirm the correct coordinate system is selected for the project. For this example, the coordinate system is NAD83, Texas North Central, EPSG 6584. I'll also keep the model storage location set to cloud mapping. Finally, I'll leave the advanced settings at their default values unless there's a specific project requirement to change them. Next, I'll select the dataset that was just imported. This tells FlightHub 2 which images to use for the processing task. I'll give the task a simple name. Before starting the processing task, I'll open the GCP settings. The first thing I want to confirm is the GCP coordinate system. For this dataset, the GCP file is using a known coordinate system, so I'll select known coordinate system. For the horizontal coordinate system, I'll confirm the correct system is selected. In this example, the GCP coordinates are using NAD83, Texas North Central, EPSG 6584. This step is important because the GCP file may still import even if the wrong coordinate system is selected, but the points may appear in the wrong location. Before continuing, I want to make sure that the coordinate system in FlightHub 2 matches the coordinate system used by the GCP file. The vertical coordinate system defaults to the ellipsoid height of the selected horizontal coordinate reference system. Before importing the GCP file, I want to make sure that the z/elevation values are prepared as ellipsoid heights to match what FlightHub 2 is expecting. If the source elevations use a different vertical reference, they may need to be converted first to avoid vertical offsets or floating GCPs. Next, I'll review the mapping settings. For this walkthrough, I'm going to choose non-standard marker. Standard marker is useful when the ground targets are supported and FlightHub 2 can automatically identify enough valid marker observations in the images. However, for this dataset, I do not have at least 5 standard markers that I can expect FlightHub 2 to automatically recognize reliably. So I'm going to use the non-standard marker workflow instead. Because I'm using non-standard marker, FlightHub 2 will first run arrow triangulation, which is the image alignment step. After arrow triangulation, the workflow will pause so I can manually mark the GCPs in the images. Once the GCPs are marked, I can run optimize arrow triangulation to recalculate the alignment using those GCP marks before continuing to the final 3D map processing. If I were using standard marker with auto mapping and FlightHub 2 automatically identified enough valid marker observations, the system could continue through the GCP matching and mapping workflow with less manual intervention. If it did not identify enough valid points, then I would need to manually mark the GCPs before continuing. I'll also leave constraint with image POS data turned on. This uses the image position data to help guide the GCP matching process, which can make the mapping step more efficient and help keep the points aligned with the image locations. Next, I'll review the mapping quality alert settings. These settings define the checkpoint error threshold FlightHub 2 uses to evaluate the quality of the final process model. These alerts are best understood as part of the final model checkpoint error evaluation rather than a separate warning for each individual GCP or checkpoint by itself. In this example, the max horizontal error is set to 0.066 feet and the max vertical error for checkpoints is set to 0.164 feet. If the final checkpoint error exceeds the selected threshold, I would treat that as a signal to review the coordinate system, vertical height reference, elevation units, GCP checkpoint setup, and GCP image marks before relying on the final output. After confirming these settings, I'll import the GCP file. FlightHub 2 supports CSV and text files for GCP import. So if the original point data is provided in another format, such as JSON, it needs to be converted into a clean CSV first. The CSV should have each point on its own row, with separate columns for the point name, X or easting, Y or northing, and elevation. I also want to confirm that the elevation column is prepared in the correct height reference and unit before importing. In the import window, I'll confirm the file settings. In this example, I'm using one skipped row, a period as a decimal separator, and a comma as a column separator. Then I'll confirm that FlightHub 2 detects the correct number of points for this dataset. It detects 10 points. Next, I'll check that the columns are mapped correctly. Once the coordinate system, point count, and column mapping all look correct, I'll click OK. After the GCPs are imported, I'll review the GCP list. Here I can see each point, its type, and its coordinate values. For this example, the points are currently set as control points. Control points are used to help adjust and improve the 3D construction during processing. If I want to independently check the accuracy of the result, I can change one or more points to checkpoint using the drop-down next to the point type. A good general practice is to distribute the GCPs evenly across the project area. FlightHub 2 also recommends using at least 4 control points and 1 checkpoint when available. Once the GCPs are imported and the settings look correct, I'll continue with the mapping workflow. Since I'm using the non-standard marker workflow in this example, FlightHub 2 will first run arrow triangulation, which aligns the images. After that, the workflow will pause so I can manually mark the GCPs in the images before continuing. After FlightHub 2 completes arrow triangulation, I'll move into the GCP marking step. Arrow triangulation is the image alignment step. Because this example uses non-standard marker, FlightHub 2 does not automatically complete the GCP marking progress. Instead, I need to manually identify the GCP locations in the images. The overall sequence for this workflow is arrow triangulation, manual GCP marking, optimize arrow triangulation, and then final 3D map processing. If any points look incorrect, appear in the wrong location, appear to float above or below the model, or even trigger quality warnings, I would stop and review the coordinate system, vertical height reference, Z units, point type, and image matches before starting the final 3D map processing task. Next, I'll manually review the GCP image matches and place markers where each target is clearly visible. For each control point, I want to make sure that the marks are placed on the correct physical target and centered as accurately as possible. I should avoid guessing or forcing marks on images where the target is unclear, because incorrect marks are going to reduce the accuracy of the final result. I'll skip ahead so I now have 6 qualified control points and 1 qualified checkpoint that I feel confident about the placement of. Once enough control points are qualified and the marks look correct, I can run optimize arrow triangulation again. This allows FlightHub 2 to recalculate the alignment using the updated GCP marks. If prompted, I can allow FlightHub 2 to remove questionable outlier marks before optimizing, especially if some matches were uncertain. After optimization is complete, I'll review the updated GCP and checkpoint errors again. If the results look acceptable and the points align correctly with the model, I can move forward with the 3D mapping task. For a first 3D map, I recommend keeping the mapping scene, mesh output, point cloud option, and advanced settings simple unless there's a specific reason to change them. Once the GCP marks and optimized arrow triangulation results look acceptable, I can continue with the final 3D map processing. FlightHub 2 will now process the dataset into a 3D map and model. Processing time will depend on the dataset size, network connection, GCP settings, selected model outputs, and selected processing options. For this video, we'll jump ahead to the completed result. Before opening the completed 3D map, I'll briefly review the processing report. This is where I can check the processing summary and review the GCP and checkpoint results for the model. I'm not going to go through the full report in detail here, but it is similar to the Terra processing report reviewed in the previous video. For this workflow, I mainly want to confirm that the processing completed successfully, review the GCP, and check for any major warnings before relying on the final output. Once the report looks acceptable, I can move on to visually reviewing the completed 3D map. At this stage, I'll do a quick quality check to make sure the model loads correctly, the coverage area looks complete, the reconstruction looks clean, and the output matches the site we expected to capture. Before bringing the 3D map into Analyzer, it's worth noting that the process model can also be used directly inside the FlightHub 2 project. For example, the 3D map can help teams review site conditions, understand terrain and structure context, support future flight planning, and create project annotations based on the latest reconstructed data. For this walkthrough, I'll keep the focus on reviewing the completed 3D model and then using Analyzer for measurements, annotations, and sharing. This review step is important because before sharing the model with the rest of the team, we want to make sure the result is actually useful and ready for review. Before bringing the result into Analyzer, I'll quickly show how the completed 3D map appears in the project map view. From the completed map result, I'll select the Overlay on Map option. This places the process 3D map back into the main project map view so I can review it with the surrounding site context. I'll pause here for a moment so you can see where that overlay button is located and what the result looks like once it is added to the map. This is a quick visual check before moving into Analyzer. The goal is not to perform detailed measurements here, but to make sure the process result is oriented correctly and ready to use for review. Once the overlay looks correct, I can move into Analyzer for measurements, annotations, and sharing. Analyzer gives us a workspace where we can review the process 3D map, add measurements, create annotations, and share the results with others. There are a couple ways to bring the process 3D map into Analyzer. If I'm starting a new review, I can choose Create Analyzer and Import. This lets me create a new Analyzer and bring the process 3D map into it right away. If there is already an Analyzer created for this project, I can also import the 3D map into an existing Analyzer. That option is useful when the team already has a review workspace set up and wants to keep all related maps, measurements, annotations, and project review items together. For this walkthrough, I'm going to choose Create Analyzer and Import. This creates a new Analyzer and brings the process 3D map in as the data source. So we can start using it as a review workspace. From here, I can choose the measurement tool that fits the review task. For this walkthrough, I'm going to choose the basic measurement of polygon. This is the best fit because we're using the process 3D map for a simple first review. It lets me outline an area of interest, calculate the size and perimeter, add annotations, and share the Analyzer with the team. I'll name the Analyzer something simple so it's easy to find later. Once the Analyzer is created, the process 3D map is brought in as the data source, and we can start using it as a review workspace. From here, we want to use the polygon measurement tool to outline an area of interest, review the calculated area and perimeter, add annotations, and then share the Analyzer with the team. For example, I can use the line measurement tool to measure between 2 points on the 3D map. This can be useful for checking access routes, estimating space between assets, measuring road segments, or reviewing distances across a job site. I can also use the polygon measurement tool to outline a section of the model. This is useful for measuring work zones, inspection areas, project boundaries, material storage areas, or other areas of interest. If I need to evaluate elevation or terrain changes, I can use tools such as point measurement, triangulation measurement, gradient calculation, surface area, or volume calculation, depending on the workflow. These tools can help make the 3D model more actionable because the team can quickly pull basic measurements without needing to export the data into another platform. Next, I'll add a simple annotation. I'll mark this location as a follow-up area. In a real workflow, annotations can be used to leave notes for another team member, highlight something that needs review, or document a specific point on the model. For example, I may want to mark an access point, a damaged area, a construction progress concern, a staging area, or a location that needs another flight or ground inspection. This makes it easier for another person to open the analyzer and understand exactly what they should be looking at. Once the 3D map review is ready, I could share the analyzer with others. To do this, I'll select the share option for the analyzer and enable sharing. Next, I'll set the validity period for the share link. This controls how long the shared analyzer will remain accessible. For example, I may choose a shorter validity period if this is only needed for a temporary review, or a longer validity period if the team needs more time to access the model. I can also choose whether to set a password. Adding a password gives an extra layer of access control, especially if the link is being shared outside of the immediate project team. Once sharing is enabled and the settings are confirmed, FlyHub 2 will generate a share link. I can copy the link, send it to the people who need to review the analyzer, and depending on the workflow, I may send this through email, chat, or another project communication channel. FlyHub 2 may also provide a QR code. This is helpful if someone wants to quickly open the shared analyzer from a mobile device or tablet by sharing the code. It is important to note that the shared link is intended for viewing the analyzer. This allows other users to review the process 3D map, measurements, and annotations without needing to manually handle the original dataset. If someone needs to make their own measurements or add/edit analysis items, they should be added to the FlyHub 2 project and given the appropriate analyzer permissions. This gives them the ability to work directly inside the project rather than viewing the shared result. This is especially helpful when working with project managers, inspection teams, survey teams, construction teams, or other stakeholders who may need to review the result but do not need to manage the raw flight data. To recap, we imported a mapping dataset, processed a 3D map in FlyHub 2, brought that 3D map into Analyzer, added measurements and annotations, and then shared the analyzer with others. Together, these tools help turn a completed drone mapping flight into a usable project resource that the team can review, measure, annotate, and share directly inside FlyHub 2.